So now let's talk about the R, L, and the C circuit. I just want to start from the series combination first. Okay. In this circuit, right, we have a resistor, an inductor, and then a capacitor. So the three of them are connected in the series and then connected with the AC source as well. Okay. So now let's assume that the current through the source is equal to, let's say, the I. Okay, the IT equal to the I naught and then times the sine of the omega t. And then the potential difference across the resistor equal to delta VR. The potential difference across the inductor equal to delta VL. And then the potential difference across the capacitor equal to delta VC. Okay. So now the objective of this topic is that we just want to find the potential difference across the three of them. So let's say delta V. On the other hand, we just want to find the potential difference across the AC source here, because you can see that this combination, right, of the RLC is just connected in the parallel with the AC source. It means that the potential difference across this combination must be the same as the potential difference across the AC source here. So that's going to be the objective of what we just want to find here, right? Okay. So one thing that you need to keep in mind is that the current through the AC source must be the same as the current through the resistor, through the inductor, and then through the capacitors. Okay. If we just want to write out the phasor diagram, right? So it means that if you just want to combine delta VR, delta VL, and delta VC together, the three of them, we have the current in the common. So let me set up, okay, the horizontal axis and the vertical axis first. So we say that the current through the R, L, and the C must be the common, for the series combination. Then let's just make the current to be the horizontal axis, okay, because the omega t equal to 0, right? So the I must be in the horizontal axis here. Okay, so let me use the blue one for the current. Okay, this with the current, the I naught in our case. Let me just make it longer. Okay, the I naught just for the current. Now, let's consider the potential difference across the R. Okay, we say that the phase of the I through the R and the potential difference across the R are the same. In this case, delta VR is must be in this direction, so this will be delta VR. So don't forget that the capital letter just means the amplitude of the potential difference. So now for the delta VL, right, the potential difference across the L is leading the current through the L by the pi over 2. So it means that if the current in the horizontal axis, so the leading phase, it just means that it must be in the counterclockwise direction, right, by 90 degrees of the pi over 2. So the delta VL must be this direction. Okay, this can be delta VL in this case, and this just making the 90 degree to each other. So now finally for the delta VC, right, we said that delta VC, the potential difference across the capacitor, is lagging the current by the 90 degree. So lagging means it will go to the clockwise direction. So then we can get that the delta VC just point to this direction, okay, and just making 90 degrees as well. Okay, so this will be the phasor diagram of delta VR, delta VL, delta VC, and the current, the I naught here. From this picture, I just write down the arrow for the delta VL longer than the arrow of the delta VC. But that's not necessarily, it can be the case that delta VC can be longer than delta VL as well. Okay, but I mean this picture, I just want to say that delta VL is longer than the delta VC. Okay, so now we say that we just want to find delta V, right? So now to find delta V, it means that we need to find the amplitude first, and we need to find the phase first, the phase difference between the current I and then the total V. So how can we solve for that? We say that for the phasor diagram, we just write down delta V and the I as the vector, right? It means that we can combine delta V as the vector as well. To combine delta V as the vector, so now you can see that we have delta VL in the upward direction, delta VC in the downward direction, right? So these two can be combined to be let's say this one. No, it's difficult to see. Okay, to be this one. So this is going to be delta VL and then minus delta VC, right? So now we have this horizontal components of the delta V and the vertical components of the delta V. So let's combine these two together. Yeah, something like this. Okay, so it means that finally this one is going to be delta V naught, right? The amplitude of the potential difference across the AC source. No, let's say across the R, L, and the C. In this case, across the R, L, and the C. Okay, and now this angle, let's say the phi. Okay, so now this phi is going to be the phase difference, okay, between the current I here and delta V, right? Delta V just be the potential difference across the R, L, and the C here, and that's it. Okay, so again, we can just write down delta V naught in the terms of delta VL, delta VC, and delta VR as well. So then from this picture, right, we can use the Penning theorem to solve for this one. Delta V naught equal to the square root of the delta VR square, and then plus delta VL minus delta VC, and then square, and then square root, right? And then square root. Okay. So now from the R, L, and the C circuit, right? Okay, where is the R? We said that delta VR equal to the I naught times the R. Delta VL equal to the I naught times the XL. And delta VC equal to the I naught times the XC. Okay. Then we can just plug in this into this equation. So we have the I naught times the R, and then square plus this will be the I naught times the XL minus the I naught times the XC, and then square, and then square root, right? And then square root. So this I naught is just the common variables, so we can just bring this out of the square root, right? Then here again we have the I naught and then the square root of the R square plus the XL minus the XC square, and then square root, okay, and then square root. So let's define here as the C, okay, as the C. So let's define the C to be the impedance, okay, of the series circuit. Okay, so let's define the impedance of the series circuit to be the C equal to the square root of the square and then plus the XL minus the XC and then square. So let's divide it here. Oops. Okay, so now you can guess that the unit of the C, right, of this is the of this impedance must be the ohm as well, because they have the R here, right, which is the ohm. So we have the ohm square and then square root, so it's just equal to the ohms. Okay. Then this circuit, this equation, right, can be simplified to be the delta V naught and then equal to the I naught and then times the C, simply like this. So now you can see that we can just find the voltage amplitude of the circuit already using this equation. So now for this C, right, can be found using this equation. Okay, so this is checked. Then later on, let's consider the phase shift, the phase difference between the current I and then this delta V. We can use the tan phi, right? We can use the tan phi. So the phase difference is, then we can use the tan phi equal to the tan just the opposite over the adjacent, right? So this opposite equal to what? Equal to this guy, and the adjacent equal to this guy. So we have that equal to delta VL minus delta VC, and then over delta VR, right? Then over delta VR. So if we plug in delta VR equal to the I naught times the R, delta VL equal to the I naught times the XL, and delta VC equal to the I naught times the XC into this equation, so you can see that the I naught just cancel out, right? The I naught just cancel out. So we have finally we have the XL minus the XC, and then over the R, and that's it. Oops, sorry. Yep. So we can get the tan phi from this equation, and then finally we can just solve for the phi here. Okay. But we said that the ultimate objective of this combination is we just want to write down the delta V, right, in the terms of the psi function. Okay. So let me just wrap up this thing again. We have the I naught in this direction, and we have the delta V naught in this direction, right? So okay, let's see. We have the I naught here, and we have the delta V naught here, and these angles equal to the phi. Okay. So then we can say that delta V, depending on the times t, right, is equal to. So don't forget that delta V is just be the potential difference across the R, L, and the C. Okay, equal to delta V naught, which is this one, and then times the sine of the omega t. Okay, so don't forget this omega t. Initially we made the omega t to be the 0, right? But now we need to bring it back here. So we have the sine of the omega t, and then plus the phi. Okay, and then plus the phi. So now this phi is going to be the phase difference between the current I and delta V here. Okay. From this picture, you can see that the phase of delta V is leading the phase of the current by the phi, right? From this picture. So in this case, the phi is for positive, right? The phi is positive here. So it means that the XL is greater than the XC. So you can just look from this equation. If the XL is greater than the XC, it means that the phi must be positive. So the phase of the delta V is leading the phase of the current by phi. Okay. But then in many cases, you can have that if you have something like this. Okay, you have something like this. So it means that in this case, the phi is negative already, right? The phi is negative already. By the way, let me just put only the sign here. Let me just put the absolute value to the phi. So it's means that we just take into account only the magnitude of the phi, not the sign. Okay. So if we have the phi to be negative, then from this equation again, it means that the XL is less than the XC, because if the XL is less than the XC, so you get the negative of this one, so the phi must be negative as well. And that's it for the series combination of the R, L, and the C. Okay, so let's look at the example. Delete the page. Okay, example. We have the RLC circuit consists of the resistor with the resistance equal to this value. So we have inductor with the inductance equal to this value, and then the capacitor with the capacitance equal to this value. So now we said that if the AC source supplies the maximum electromotive force, okay, EMF just stands for the electromotive force of the 150 volts with the frequency of the 60 Hz. So answer the following questions. Okay, so we can just use the previous picture here, right? So we have the R, L, and the C in the series combinations, and we have the AC source here. In this question, it just gives us the what? The 150 volts of the AC source, right? It's going to be the maximum EMF. So it is this value delta V naught equal to the 150 volt. Okay, and then we also know the frequency of the source equal to the 60 Hz. So we know the F, the frequency is equal to the 60 Hz. So now for the part A, we just want to find the XL, XC, and then the C, right? To find the C, we need to know the XL and the XC. But then to find the XL and the XC, we need to know the omega. Okay, we need to know the omega. So then the first of all, let's just find the omega, the angular frequency. Then from here, we have that the omega equal to the 2 pi times the F, right? So the F, the frequency, just equal to the 60 Hz. So then equal to the 120 times the pi Hz. Okay, so let me just give the answer in terms of the pi here. Oops, sorry, not the Hz. It should be the radians per second. It should be the radian per second here. Okay, so let's just start from the XL. Let's just start from the XL. the XL is equal to the omega times the L, right? XL just equal to the omega times CL, equal to omega just 1/2 times the pi, and then the L equal to the 1.25 Henry. This is inductance. Okay, so the answer is equal to 471 ohms. Now for the XC. The XC is equal to the 1 and then over the omega times the C, right? Equal to, okay, so let's just put in the number 1/2 times the pi. So now for the C, it's just the 3.5 microfarad, okay? So the 3.50 micro is 10 to the negative 6. So, okay, so don't forget this prefix as well. And then 1 over this value. So then if you use the calculator, you will get the value to be the 758 ohms. Okay, 758 ohm. Now finally for the impedance C, okay, the question is the square root of the R square and then plus the XL minus the XC and then square equal to, what is the R? The R is the 425 ohms, okay, just plug in the 425 and then square and then plus the XL minus the XC. So we have 471 minus the 758 and then square and square root, right, and then square root. The answer is equal to the 513 ohms. Okay, the 513 ohms. Okay, one thing that you can notice is XL, right, equal to this value and the XC equal to this value. So now you can see that the XC is greater than the XL. Then you may guess that from this picture, right, you may guess that the phase of the current, current should be leading the phase of the potential difference across the source by phi, right? So finally we should get this type of the picture here. Okay, so now for the part B, we just want to find the maximum current in the circuit. Okay, it means that we just want to find this I0, right? All this I0, the maximum current of the circuit. Okay, but what we find here is we know the delta V0, right? The maximum EMF across the source, and we know the C. Then to find the I0, we can use this relationship between the maximum electromotive force and the maximum current to find the maximum current here. So then we said that the I0 equal to delta V0 and then over the C equal to delta V0, right, just the 150 volts, and then over the C just the 513 ohm. So then you can get that the I0 just equal to the 0.293 ampere. This is the answers. Okay, part C, we need to find the phase difference between delta V and the current I. Okay, so now you can see that we have this current, right, and we have this delta V. Okay, and we know that both of them we have the phase difference. So what is that value? To solve that, we can use this equation to solve for the phase difference between these two. So we say that the phi here, right, equal to the arctangent of the XL minus the XC and then over the R. Okay, so let's just plug in the value into this one. We have the arcstan of the XL is what? XL is 471, XC is the 758, right? 471 minus the 758, and then over the R just 425. Okay, so the answer that we can get is equal to negative of the 34.0 degree. Okay, so I mean just write out the phase difference in the terms of the degree, not in the radian. Then again, right, we get the negative value of the phase. It means that, okay, it means that, so just compare to this picture, it means that the phase of the current is leading the phase of the delta V by the value of the phi. Okay, so we have here the current, right, equal to 0.293 ampere, and we have the delta V naught equal to the 150 volts, and the angle between these two just equal to the 34.0 degree. We can also write down the current and delta V as function of the time as well. For example, the current I, right, equal to, okay, so let me just use this form. Where is it? Let me just use this form for the current, okay, and let me just use this form. Where is it? Oh, I haven't write down. Okay, that's fine. Let me just use this form for the current. So we said that the I equal to the I naught, right, 0.293 ampere, and then times the sine of the omega t. Omega just 120 pi in the unit of the radian per second, right? This is the omega, and then times the t. Okay, so this will be the sine function and the current. So then how about delta V, the potential difference across the R, L, and the C? So here we have delta Vt, right, is going to be equal to, okay, the maximum value is 150 volts, and then times the sine of the, okay, omega t, okay, omega just the 120 pi radian per second, and then times the t. This is the omega t, and then plus the phi, okay, and then plus the phase difference between delta V and the I. But in this case, the phi is negative 34.0, so here we have the minus the 34.0 degree. Okay, so that's going to be the function of the potential difference across the source, or across the R, L, and the C's in the series combinations. Okay, so now for the part D, we just want to write down delta VR, delta VL, and the delta VC, right? In the terms as a function of the current here, okay, as a function of the current, okay. It's just the same as I mean we write something like this, okay. So this is delta VC in terms of the time. So this will be the delta VL in the terms of the time t, and this will be the delta VR in the terms of the times t as well. Okay, so let's just start from delta VR first. So delta VR equal to delta VR, right, and then times the sine of the omega t equal to, okay, delta VR equal to what? Equal to the, so we don't know the delta VR here, but we know the maximum current and we know the resistance, right? So delta VR just equal to the maximum current and then times the resistance here. Okay, we have 0.293 ampere for the maximum current, and the resistance equal to the 425. Okay, and then times the sine of the omega t. So I don't need to plug in the omega, okay, because we know already that omega equal to this one. So let me just leave it as the omega here. Okay, then equal to 124 volts, and then times the sine of the omega t. So this is going to be delta VR, the potential difference across the resistance as a function of the times t. So now how about delta VL? Okay, how about delta VL? Okay, we can use this one to find the delta VL, right? So let's say that equal to the delta VL and then times the sine of the omega t and then plus the pi half. Okay, so don't forget that the phase of the delta VL is leading the phase of the current by the 90 degree. So that's why we have the positive pi half here. Okay, equal to we don't know delta VL, but we know that delta VL here equal to the maximum current and then times the XL, right? So the maximum current is 0.293 and the XL is just equal to the 471. Okay, and then times the sine of the omega t plus the pi half. So then finally we get that equal to the 138 volts. Okay, 138 volts times the sine of the omega t plus the pi half. So now finally, okay, finally for the delta VC, okay, we can use this relationship to find the delta VC. So we have delta V capital C, right, and then times the sine of the omega t minus the pi half equal to, okay, delta VC equal to the I naught times the XC, right? The I naught just 0.293 and the XC is equal to what? 75x ohm. We have 75 the x ohm, and then times the sine of the omega t minus the pi over 2 here. So then the answer is 222 volts, and the sine of the omega t minus the pi over 2. Okay, so here we get the potential difference across the R, across the L, and across the C as function of the times t here. Okay, and now from the part C, right, we get the potential difference across the combination of the RLC as this one. So then you can guess that okay, delta V here, right, as function of the times t, so it is this one, must be equal to the potential difference across the R plus the potential difference across the L, and then plus the potential difference across the C. Okay, so this equation will work for any time t. So you can check by yourself. I mean, you can just plug in any time t. So you can just plug in any value of the time, right, to this one, and compute to get a value, and you can just plug in that term right into this one, and sorry, this one, and this one, okay, and then sum up together. So you can see that both sides of the equation must be the same, okay. But just keep in mind one more thing. Delta V naught, right, which is the maximum amplitude of the delta V, is not equal to delta VR plus delta VL and then plus delta VC, okay. So you cannot sum up, the amplitude of each of them together, because what? Because the delta VR, delta VL, delta VC, and the current, right, all of them has the phase, and the phase are different, so that's why you cannot sum up. Actually, we have this relationship already, which is this one, right? Where's that? Which is this one. So if we just want to find the delta V naught, it's just the square root of the delta VR square plus delta VL minus delta VC and then square, okay. This is the correct relations. This is wrong, okay. So you cannot do something like this one. Okay, next, let's talk about the RLC in the parallel combination.